All right, today we're going to talk about model evaluations and machine learning. Now, what we're going to discuss in a brief is the machine learning process and how do we evaluate a machine learning model if it's going to be good or not good for our use. So one thing we're going to, let's go ahead and execute this initialization block in our code. And I want you to take a look at our basic machine learning process. So on the left, we have data sources where we extract data from. And so we have a data collector. Once we collect it, we have to clean it, transform it, create some features, normalize it if needed. And then we're going to build a model. Now, we're going to tune that model, and we also have to validate that model. Now, here is a decision, what's here in the red circle. We ask the question, is this model acceptable? If the answer is yes, then we go ahead and deploy it, which makes sense. But if it is not acceptable, we have to go through our recursive cycle one more time, perhaps do some more cleaning, transformation, etc. We may also have to do some different tuning on our models. But what we're going to focus on today is actually what's in that red circle is how do we measure a model? Or how do we measure a model's performance, and then how do we determine whether it's good or bad, right? And by the way, all of this is rather subjective. So we'll go ahead and kind of walk through this today, and it'll start to make sense as we process it. So the first thing I want you to learn about is something we call a confusion matrix, and it's actually this picture here. Down below, where on the left-hand side we say we have predicted values. On the upper side, we have actual values. Now, the predicted values is what our machine learning tool or machine learning model is going to predict. The actual values are what they should have predicted, given the fact that we actually know the result, right? So, for example, if a machine predicts something as positive, it's actually positive. We call that a true positive. If the machine predicts something as negative and it's negative, we call that a true negative. That's pretty straightforward. But if it predicts something as positive, but the actual result is negative, we call that a false positive. It's like saying that somebody has cancer, but they really don't, right? That would be a false positive. And if the machine predicts as it being negative, but in reality it's a positive, so the machine says, no, they're clear of cancer, but they actually do have cancer, that would be a false negative. So this is a confusion matrix, and we actually count the number of records that actually exist in one of these four areas. So let's take a look at a basic confusion matrix example that we're going to use here in Python. And sklearn has a tool that we can use, and simple enough. It is, the first one is the confusion matrix, and the second one is going to be the confusion matrix display. Let's see here. All right. And what we have here on lines 5 and 6 are just examples of data that we might have. Now, the first line, let's say, is the real case of an output. All right. This is going to be a dependent variable y. And then the line 6 is what the machine predicts what the y should be. And we notice everything is mostly correct, except that we do have a case here where the machine predicts it differently, and of course right here. So there are two cases where there may be a false positive and or a false negative. So let's go ahead and apply that confusion matrix tool, that function of y true and y predicted. And what we're going to do is we're going to use the ravel method inside our confusion matrix to be able to produce the true positive, true negative, etc., etc. So always remember this. This is always going to be in this order. It'll be true negative, false positive, false negative, and then the last one, of course, is true positive. All right. So when we do this ravel function, we always need to have 4 variables to the left of the assignment symbol, so that way the proper output gets assigned that way. And what we're going to do when we display this, it's always going to be displayed in this fashion, where true negative is going to be up in the upper left-hand corner and in true positive in the bottom right-hand corner, and so on. You can see what's listed there in lines 12 and 3. So then let's go ahead and then let's print that CM example. All right, so now we can see that the confusion matrix in this particular case is there are 3 true negatives, 1 false positive, 1 false negative, and 10 true positives. And we can see that if we look at this data up here, we can see that it is relatively true. An alternate way of displaying this is to use our display tool. So we have our confusion matrix display option. And what we can do is just take our confusion matrix example and plug it right into this. And I put all the other pieces together for you, and it basically makes a pretty display of the confusion matrix. And you can see it is identical to the one up above. The only difference is it has colors, and the colors actually have meaning about quantity. All right, so this is just based on occurrences of the predicted results based on the data that was put in. Now we're going to start to take a look at metric scores that will have meaning based on our confusion matrix. So we're really going to be looking at the count of true positive, true negative, false positive, false negative. And we're going to call accuracy basically the true positive plus true negative all over the amount that was put in. So how much of it is true? That is accuracy. Precision is how well does it say things are positive or true positive. And then for recall, we're going to see how well does it predict true positives. And specificity is actually the obverse of that, where how well does it predict true negatives. And an F metric is actually a balanced metric between precision and recall. And it is a geometric mean value, which I have published here. It's 2 times precision times recall divided by the sum of precision and recall. So we're going to use these metrics to be able to identify how well a model does. And we'll explain how all these pieces get put together. So let's start. Once again, we have our true negative, our false positive, our false negative, and true positive. That's always going to be in that order. And we're going to ravel or unravel the items. Now, what I've done here is I've put the mathematics that is in the display up above here into these functions right here. And basically what we're going to do is we're going to display those, and I want you to see what those metrics become. So we can now see that our true positives, this is the same thing we saw in our confusion matrix. And based on what we had before, the accuracy is 0.86. Precision, recall, and F score are all 0.909, and the specificity is 0.75. Now, in some cases, this could be a very good result. And of course, since these two are the same, F score is obviously going to be the same given it's a geometric mean. All right, so taking a look at these values, we can see that the scores are typically between 0 and 1. The higher they are, the better they are. So if we got a perfect 0.99 or just a 1.0, then we would know that we have a really good model. Now, in a lot of cases, people will use the F score as kind of a general score to kind of evaluate models to models until they can really assess where the risks might be. So for that reason, we might just go ahead and calculate the F1 score by using the function from sklearn called the F1 score, just evaluating the true and the predicted, and you can see it's going to give us that result. All right, so to make our days easier, I have started a model performance function that we can create. And simply what we're going to do is we're going to take what is up here in the previous block. We're going to copy it. And we are going to paste it right here. Now, this will end up becoming our model performance block. The only thing that we have to change here is, notice the input variable is a confusion matrix, and we have to make sure that right here we also changed line 5 so that way it has the confusion matrix right here. That way the input confusion matrix here gets raveled into these components, and then we have all those evaluations. So once again, if we, just to test this out, if we put our CM example in, we can see that we get basically those same results. All right, let's think about why each of these is important. Well, in general, we're going to look at precision as something that emphasizes the predicted positive cases, which is value if there's high risk to predicting false positive. What that basically means, if you get a result where a positive indicator could be could be a high risk thing, such as loaning an individual a lot of money, like in a bank. So, for example, if you had somebody that was high risk, but they got put into, let's say, a machine learning model, and the model said, yeah, they're going to be okay to lend to, but in truth, they were risky to lend to. And so a false positive in this case could be a high risk scenario for a bank. So a bank might be looking at like credit information and looking at a precision score for a model at the highest level because they want to be able to protect themselves from the risk from creating false positives. Recall emphasizes the labeling of actual positive cases, where if there's a false negative, there could be risk. And that could be something, as we've mentioned before, situations with like cancer patients. So if a model doesn't predict somebody with cancer, but they actually do, then they might not get the treatment that they need. So this would be a false negative. And in these cases, recall might be more important. So you always have to look at precision and recall in the light of what you're actually analyzing. Now, this is why people use F-metric, is because it's a geometric mean between precision and recall. And so it really helps you kind of get a general sense of the model, assuming that precision and recall are doing relatively well, or they're both important. Now, some people will sometimes ask, why are we not looking at accuracy? Well, accuracy just tells us how well it's detecting the true things, right? But it really doesn't balance out our risks. So precision and recall tend to be the things that we look at a lot more when we look at models. So let's go ahead and load the data. By the way, in the zip package, I have your data included. It's the credit risk data. And let's use pandas and read the CSV. And let's look at what we have here. So we have a little bit over 150,000 records, and we have 10 different attributes that is related to this data. All right. And if you'll notice, one of them is a binary variable, which is bad or good, meaning are they a bad customer or not, right? Can they be considered high risk or low risk? So let's train a model based on all of these other characteristics that are available and determine whether we can create a model that will determine if somebody could potentially be a bad or high risk customer versus not. So let's do some basic descriptive analytics first. So down here, we're going to ask to describe this data and print out all those values. So here we can get a general sense of all of our data. So customer number is just an index, so we're not going to worry about that too much. But bad, we can see that on average, right, we have 0.07, with the highest being 1 and the low being 0. Okay, well, there's not a lot in between. But we can kind of see how all those pieces end up going together. We have credit limit, late payment counts, et cetera, et cetera. Okay. We also have ideas about like monthly income, where one person, the highest paid person, gets $135,000 a year, and the lowest paid is $1,000. Or maybe this is monthly income, excuse me. So monthly income, that's $835,000 a month. All right. So this is the data of the credit values that we have. And let's start looking at how we're going to apply this in a machine learning scenario. So with typical machine learning models, we have a pile of data, and we need to split it into two pieces. We'll take all of our data and to split it into training data and test data. And by the way, this should be done randomly. And we do have tools that will allow us to do a fair random selection of our data set. Generally, we might use a rule of 70% training and 30% testing, but that's not always the case. It really depends on the data that you have and how well your model needs to be trained. All right, but in this case, we're going to use 70-30. So the reason why we do this is we can assume that all the data that we have is somewhat homogeneous. So for example, customer behavior for 1 year will be identical to the customer behavior in another year. Now, to offset any kind of situations that might be seasonal is why we randomly select from, let's say, 2 different years on the type of data. And that random selection should take out any kind of scenarios with seasonal data. But the whole idea is that we have a homogeneous block of data and we split it into two halves. We have one that we train our model with, and then we have one that we test our model with. And this is just to make sure that the testing data is not the training data, because the training data is what basically is the answers to the test, and the testing data should not be those answers. All right. What we're going to do first is we're going to define our independent variables. And I have these 1, 2, 3, 4, 5, 6, 7, 8 variables that I'm calling the X independent values. And these will come from our data frame of our credit risk data. And our Y variable is going to be basically bad. This is what we want to predict. Okay. So we're going to take this data. We have our X data and we have our Y data. And we're going to use this train test split function. And I mentioned that we're going to only have a test size of 30%. So this is a 70-30. And to make sure we all get the same values, I'm going to set the random state to 42. Now on the output of this model selection, if you have two variables that you put in, there will be double that coming out. So if I have an X and I have a Y, and I have a Z, for example, that would be 3 in. That means I would get 6 out. But since I'm only putting 2 in, right, I am only going to get 4 out. So let's kind of put those in this function. First, the first variable are the X variables, right? So the first is always going to be the training portion, and the second will always be the testing portion. So I'll have X train and X test. My second variable is Y, so once again it's Y train and Y test. All right. So that is based on these two variables that I'm putting into this particular function right now. So let's look at what the X training shape looks like. Let's look at what the Y training shape looks like. We're going to compare those two. We're also going to look at the shape of the X testing data as well as the shape of the X training data. Oh, I spelled it. Y training data. I apologize. So now what we see here is that we have eight variables and we have 105,000 records, 105,005 records. Here we also have the same number of records, but notice that there's no variable following the comma here is because it's only one variable, which is the dependent variable. Now, down below, looks like I did something wrong. Actually, it's right here. This should be Y test. Y underscore test. I'll try that one more time. There we go. So now looking at the testing data, now we see that we have the same number of records. So everything is what we would consider to be symmetrical. All right, so here's our basic logistic regression model. And we're going to use sklearn to apply this logistic regression model. And we're going to approach this somewhat from a machine learning view, not a statistical application view. So with that, we're going to take this model, which is here on line 3, and we're going to apply a fit of this model based on the training data. So we have our X training values, And then we have our Y training values. And our intercept for our model, if we really wanted to see these components, it's going to be the intercept with underscore at the end, and the coefficients will be the coefficient with an underscore at the end of it. All right, so I have the rest of the block filled out for us, and let's kind of run this model. It's going to take just a small smidge of time to do the fit. And I spelt coefficients wrong, didn't I? Yeah. It's not CEO, it is COE. My bad. There we go. So now what's going to run, it should produce our result here shortly. I apologize for that error. So here are all of our coefficients, including the intercept. And this is basically what our model looks like. These are the beta coefficients. But now we want to use this model to predict an outcome based on what we have in our test data. So now here we're going to take our X testing data, X underscore test, and we're going to predict a Y value from this. Now, once again, we're going to use our confusion matrix tool, and we're going to look at what that Y predicted value is in respect to our Y testing data, right? And we're going to print the testing evaluations, and we'll also put this into our function CM testing, and let's see what ends up happening. All right, so we get our confusion matrix, and here are the results. We have really good accuracy. We have good, not great precision, really poor recall, but a really bad F1 score. So as I mentioned, precision might be something that we would want to look at from a bank credit point of view. So let's see if we can make some improvements. Let's take a look at something though that we may have skipped. Let's get a value count of how many are bad. So we're going to use this little function in pandas, and I said value counts with an S, called value counts, and we can see that out of all of our data, there's only 10,000 that were considered to be good. And when you think about that from a grand scheme of 150,000 records, that is barely, was it 7% of the total number of records? So we have a little bit of a biased value here. So let's take a look at prediction probability situations. So we're going to look at the prediction probability against our X test values. And let's go ahead and take a look at the shape of this. And here's what we have. So here we have a record of customer number and the probability that it is not bad credit, and the probability that a person does have bad credit. And when we kind of start to take a look at this, we can see that the probability scores on the far right tend to be rather small. So what we need to do, or one thing that we can do, is the default value for looking at what goes into, let's say, a bad credit or not bad credit scenario, is looking at this probability value and saying, it's more than half, so it's bad, or it's less than half, so it's good, right? So what we're going to do is we're going to create a threshold. Let's do a couple of things. You don't need to make full sense of all of this. We're going to take the predicted probability of what is in this value, and we're going to set a threshold of 0.5. And this should actually come up to be the exact same result, but I'm going to prove it to you by using the 0.5 first. So basically, if the probability as bad credit is less than 0.5, we're going to put them in one category, and then if it's greater than 0.5, we'll put them in the other. So we're going to apply a small confusion matrix with our Y test here. based on the predictions of what comes out right here. All right. So then we'll go do the performance here of the bad credit component from line 12. All right. So we can see here's our confusion matrix. Our default threshold is 0.5. And let's take a look at these results. And they're pretty close to what we had before, right? So that was just showing you that this threshold value that we have set up here is basically already at a 0.5 threshold. So let's make a change. Let's change that threshold to 0.2. Now I left everything the same except for this one right here, just so that way you wouldn't work too fast ahead of me. And that is going to be the y-test values. And let's take a look at what the result is for the 0.2. So if we put a 0.2 threshold on probability scores, we can see that our precision goes down, but our F1 score increases. So this might be an advantage. Okay. Well, let's maybe make another change. Let's try going to threshold score of 0.1, and let's see what this does. So again, this is going to be against the y test, and threshold of 0.1. Our precision is at 0.2. Our recall is up, but our F score is at 305. Getting better, maybe not. I'm not sure. All right, let's try one more. We're going to try a new threshold score of 0.01, right? And I filled in all the pieces for you, so we only have to hit go. And at 0.01, our F score starts to tank again, and our precision goes way down, but our recall goes way up. So let's kind of take a look once again at our definitions. And I have them here. I thought I had them here. I want to go above the regression where we have, here it is, precision and recall, okay? So in our particular case, we are actually not predicting false positives, but we want to make sure that we are not producing false negatives, because our prediction value in this case of 1 would be that they are bad credit. Right? So now we actually want to emphasize our recall in our particular model. So basically, we don't want to say they have bad credit and not give them any kind of money. So remember, our prediction value here is 1 would equal bad credit, right? So that's one of the things, we don't want a false negative. So that's where now when we look back at our model, we now have a recall of 0.99, which is really good, even though our F score is pretty bad. But I will tell you one thing, that even though that our recall is really high, it might be in a situation where basically some people are still getting bad credit. And we want to take a look at balancing out also our accuracy. So even though our recall is fantastic here, our accuracy has dropped. So I am not going to recommend to go with a threshold of 0.01 because I know this ends up tanking quite a bit. If I go back and take a look at certain things, I can see that 0.1, I have decent accuracy, I have a decent F score, but I have a recall of 0.5 or almost 0.6. All right. So I actually might make a decision to go with a threshold score of 0.1 and try to manually filter out those that end up being called bad credit just to make sure and confirm that they are bad credit. Okay, so, but think about what this tool will provide for us. It'll actually cut out about half of the work that people would do manually nonetheless. So that's pretty helpful. All right, let me show you a couple of other tools. A lot of times people will want to look at the evaluation of something based on what we call area under the curve. So let's go ahead and import a ROC curve, or which is the receiver operating characteristic curve. And AUC a lot is the area under the curve. And let's go ahead and let's do some evaluation of our ROC curve based on our 0.01 data, right? And we're going to do some plotting here. I have all the other pieces put together. And this basically gives us our result of how good our model really is. Now, if we take a look at the red dashed line, that area under the curve is supposedly equal to a fair flip of a coin. So we consider that 50-50. So even and where we are with our situation, right, is we looked at Y probability 1, which is actually right up. Where do we create Y probability 1? Here it is. We have Y probability 1, which is basically these values here, which is probability as bad credit. So now we can see this area of the curve when we evaluate Y probability 1 under Y test, we get a little bit better than 50%. And in some cases, this might be sufficient if we're going to add to our business process some manual operations. So this could also be workable. All right. Now the ideal ROC curve is a little bit more square, where the blue line would go almost straight up, maybe have an elbow at like 0.9 and then go straight horizontally from there to the right. Okay. So in general, we want our area under the curve to be greater than 50%, which is going to be better than random guessing. And currently, we have an area under the curve of 0.81, right? And we always have to be careful with our data. And we also have to be careful about overfitting and also underfitting. All right. So overfitting is an idea like what we saw when we started looking at different threshold values that, for example, we were really heavy looking at recall, but then the accuracy started dropping, right? So we can see that with the accuracy starting to drop, but our recall being really high, we had an overfitting situation. Now, underfitting is where we have weak performance, typically no matter what we do. We have to keep trying, possibly with some different revisions. But overall, we have to be looking at both our F scores, our precision recall, and our accuracy all in one. Now, what I have here is I have basically, I believe I put everything together for us. So let's this is a summary of everything that we've been dealing with. So let's go ahead on line 7. We're going to go ahead and do a logistic regression one more time with our, with our X-train data. And we're going to compare that with our Y-train data. This is our default. And we're going to evaluate the performance based on that CM training value here on line 8. And then we're going to do the predicted probability of our X-train. There we go. And then we're going to change the threshold to 0.01, and we're going to also look at what that comparison comes out to be. And so now we have some comparison model items that we can look at. There we go. Oh, what did I do wrong? Oh. It should be Y-train. Let me see what my error is here. It's saying my error is incorrect right here. There we go. Now we have our comparisons, and we can see that when we look at the default threshold of 0.5, we have decent accuracy. We don't have great precision or recall, but this would be a basic scenario where we have performance of 0.01. We also have really bad accuracy. So let's compare, for example, 0.05, and let's change that threshold from 0.01 to 0.1. And now let's go ahead and compare the two. So so now if we're comparing 0.5 to 0.1, we lost some of accuracy, but it might be better than expected. Our recall has went up, but now our F-score is much higher. So a 0.1 threshold might give us something better to work with. And that's kind of the things that we've been speaking of so far. So this kind of concludes our lesson dealing with machine learning and how to evaluate models using all of our metrics, the accuracy, precision, recall, specificity, and F-score. So this will help us as we start to develop tools that will help us predict outcomes in our text analytics course.